Good morning, everyone. So I'm going to work with this one, right? Not with it. So I'm actually an author of an incredible book with this gentleman here. So that you haven't seen yet because it's not out, but this is going to be my most prestigious publication. So first of all, it feels home to be at ZIB again. And in particular, CO at Work has been like one of those events every few years that definitely put together the future of computational optimization. So the future is your hands. It's not in my hands anymore. So please keep going. And this is what I will talk about today is kicking off this machine learning day that will have fantastic speakers in the rest of the morning and afternoon, is giving you an overview of what we have been trying in the last 10 years to bring machine learning to help branch and bound for mixed integer linear programming, even if I will switch to some side of mixed integer non-linear programming as well. So this is actually joint work with Lara Scabuzzo that this is part of this survey is part of her PhD thesis, and her advisor, which are Karen Ardile and Neil York-Smith in Technical University of Delft. So this is I've studied the program, so you have seen already some form of, let's say, talking about machine learning in this context. Definitely the last 5 to 10 years have been such a, big push and move of machine learning for combinatorial optimization. And of course, this is motivated by the incredible success of machine learning, especially in areas like image recognition, language processing, games, and count. And the successes led to some, let's say, many communities, scientific community, to ask if some of the techniques developed within machine learning could have been used for in their own domain. And of course, combinatorial optimization is one of them. And I will try to actually help you understand what has been done so far with this overview. And Timo later and some of the other speakers will definitely go much more into the details of this. So the outline of the talk is I will briefly remind you whatever you have done in the first week and about mixed integer linear programming, and then I will tell you the mixed integer linear programming at the time of artificial intelligence, so kind of methodological directions in which the use of machine learning is changing or will change, question mark, MILP computation. I will try to finish with the perspective, challenges, and opportunities, which, I don't know if I will have the time, but otherwise we can take it in the coffee breaks and whenever there is time. I'm here until the end of the day for sure. So this is a schematic overview of how much interaction there have been between combinatorial optimization and machine learning. This is a slide that I actually borrowed from Neil. And there have been 2 surveys relatively recently, because indeed the field goes so fast that I wouldn't say that this survey that I wrote with Joshua Benjo and our student Antoine Provost is the state of the art anymore. But I mean, these 2 surveys have been kind of influential in start to picturing what was going on in the first at the beginning. So you can see a lot of interaction in many contexts of combinatorial optimization, augmented machine learning. So the opposite of what we are looking at today, because what we are looking at today is instead the situation in which we want to augment the use of machine learning, the combinatorial optimization by machine learning. And indeed, this is actually what I will try to highlight today is how machine learning can help, in particular mixed integer linear programming, in pretty much every building block of a solver, from let's say, try to looking into this from a methodological perspective, while I think Timo will very much go deeper into the area. So this is based on this survey that we wrote, the keynote that I gave at ISMP in Montreal last July, and now it is a mathematical programming paper in DOI version E, and hopefully at some point we will publish the entire issue. Of course, I guess after, since we're kicking off the second week, I don't need to give motivation for mixed integer linear programming. Some of them are in this picture. And in terms of how it works, also, now you should be proficiency on doing this. But let me remind very quickly the game, because that is what we will approach in the entire rest of the talk. So if I'm looking at minimizing a linear objective function over a set of linear inequalities with some of the variables, for example, the first p variables are required to be integer, then the game is I'm trying to get two different trajectories to actually intersect. The first trajectory is the red one here, which is the one of the primal bound. So I want to improve the feasible solution until a point in which I reach optimality. And on the other end, I have the dual perspective. So I solve the LP relaxation, and I have a blue trajectory here that is going up. And of course, I don't know the optimum a priori, so I only know the optimum when the two trajectories intersect. Okay? So now, at any point in time, I can measure the gap between the first trajectory and the second trajectory, and I can represent my problem, actually, I can represent my solution method in a tree that is defined by the LP relaxation here. So I'm dropping the integrality requirement of these variables, and then I start essentially doing things on the LP, so on the LP relaxation, and I'm actually keep going by at some point splitting the problem into sub-problems, which are the operation that I'm doing by branch. So the key features of mixed integer linear programming being covered by Timo last week are preprocessing and configuration, then cut-in-plane generation, sophisticated branching strategies, and primal heuristics. Of course, there is much more, but that's the core. And I'm not going to spend time on those, but just quickly thinking about this is the way in which I think about preprocessing and, let's say, terming configurations is thinking about whatever you want to do in order to be more effective later on. So like reducing the size of the problem by understanding some connections between the parts of the variables and maybe removing constraints, and configuring your system, mixed integer programming solver, in such a way that later on is going to be more effective. Okay? So cut-in-plane side, we know now, we solve the LP relaxation. This point is not integer or not mixed integer, not integer in this case, in R2. And then I want to actually generate linear inequalities that are cutting off the fractional solution and eventually strengthen, so making the LP relaxation going closer and closer to the convex solve of feasible solutions. So there are many families of cut-in planes which are used regularly into branch and bound, and they differ in the way in which they are devised, in which they are separation. The separation works. Separation is this operation of asking an oracle if the solution, if there exists an inequality in a certain family that is actually cutting off that fractional solution. And when this inequality is found, somehow adding it to the LP relaxation. And there are many ways of doing this. Pretty much everything that is in the solvers is based on aggregating the original constraints, having a so-called Bayes inequality, and applying some sort of operations to the Bayes inequality in order to get a cut. And you may end up with a large number of cut-in planes, and those cut-in planes you have to do cut selection, so finding with the ones that you really want to add to the LP relaxation. Otherwise, If you add too many of them, the LP is going to be slow, and at the same time, you can encounter a numerical instability. Branching, again, if this is the optimal solution of the LP relaxation, then you want to split your problem into sub-problems. At some point, you don't want to do any more cutting planes, and then you want to split your problem into two sub-problems. And depending on the variable you decided to branch on, which branching operation means you take the solution here, one variable which is supposed to be integer and instead is fractional, and you split the problem into sub-problems by rounding up or down the value of that particular variable and imposing two constraints, which are disjoint, and the optimal solution, of course, is on one of the sides. So the interesting thing here is that we don't know mathematically we don't have a mathematical understanding of what is good and bad here in branching. So ideally, I mean, in theory, you can take any variable and branching on it, and then the algorithm will converge to the optimal solution unless special cases arise. And the currently best method that we know is called strong branching, in which you pretty much simulate the branching on any variable, and you pick the variable that is actually giving you the best improvement with respect to the current solution. Of course, this is too expensive because you have to take all the the fractional variables, solving two LPs, and then deciding about that at every node of the branch and bound, which is actually, I mean, just huge. And so this is combined with some other interesting rules in something which is called reliability branching that maybe you have covered extensively. The last block is, I just give you a pictorial representation. This is KIP. This is actually the number of every one of those balls here is different primal heuristics. So primal heuristics are the algorithms that you're running in order to make the trajectory, the red trajectory that I've shown you before, to go as fast as possible. Okay, and then there are many of them, and then the question is how to use them, how to devise them, and so on and so forth. So what is the opportunity here? The opportunity is that we have at least two pain points that mixed integer linear programming and solving a mixed integer linear programming problem is, reaching or is encountering, which is that some operations are just too long. So we know how to make decisions. So you can think about mixed integer linear programming solver or mixed integer linear programming technology as a huge amount of different let's say, decision problems that have to be solved in order to put all these pieces together, right? I mean, branching, cutting, how much to do preprocessing, and which type of preprocessing you want to do, which heuristics that you want to run, and so on and so forth. All these are decisions that have to be made. And the question becomes, some of these decisions, we know how to do them in the best possible way. So we have a very good mathematical understanding of how to make each one of these decisions, except that some of them are just taking too long. So if we want to use the mathematics behind the scene, it may end up that it takes a lot of time to make one single decision, and without, I mean, taking a, let's say, a heuristic version of it, or even like skipping that part completely, would have maybe led to solve the problem much faster, right? So the situation is there are places in which those decisions are too expensive to make. And there are other places in which the decisions are too heuristic. So we don't really understand which one, how to make that decision in the optimal way. Okay, this is a mathematical luck. So we don't know, and branching is one of them. We don't really have a full understanding of how to make the branch and bound small as possible. Okay, the size of the branch and bound as small as possible. We cannot characterize that. So these are the two pain points that we're thinking about. And if you think about it, indeed, in variable selection, so which is again the problem of deciding which variable you want to branch on, the situation is that we have both problems. So we don't know mathematically what's best, and actually we don't know how to characterize best at all. And the thing is, so it's too heuristic in a certain sense, since we don't have a mathematical understanding, it's very heuristic. On the other hand, the best heuristic that we have is actually even too slow, right? I mean, it's like it will require to actually compute P, recall that I said that we have P integer variables. In worst case is at every node, I have to take the P variables that are all fractional at the same time, rounding them up and down, solving twice as many LPs, just to make one single decision, which is the next variable to branch on. So this is probably the most obvious place in which you can think of for these pain points to appear, because indeed this decision is both heuristic and at the same time with the heuristic that you have is slow. So now the question which has been appearing in the literature for the last 10 years is, can machine learning methods as imitation learning, reinforcement learning, and the deep learning techniques that in architectures that have been developed continuously for other type of problems help combinatorial optimization, in particular mixed integer linear program, to actually deal with a situation in which we are too slow or too heuristic. And of course, those architectures most of the time and those techniques have been developed in a completely different context. So the question at the very beginning, 10 years ago, was, I mean, can we even learn from data what, from the data produced and collected in the context of discrete optimization or combinatorial optimization, can we learn patterns that will be helpful in our context? And of course, the requirement that we want to keep is that the mixed integer linear programming technology is inherently exact. So we want a modulo, let's say, tolerances and computation in floating point arithmetics. So I don't know if Ambrosch is going to talk about exact MILP. He will. Did you already talk about this? Okay, that gentleman over there is going to talk about exact MILP, in which at some point you want to avoid the errors from in floating point arithmetics. Let's assume, leaving that aside, the algorithms are converging to optimal solutions. So, and actually, first of all, to feasible solutions. So feasibility and optimality are a requirement that with technology we want to keep. And so the question is, if we switch to do things in statistical learning ways, so we don't want to lose that guarantees. So we have to use that with a grain of salt. So there are two learning methods which are relatively standard, but they have been applied to mixed integer linear programming. One is demonstration. So the idea is that whenever you have to make a decision, you have an expert, and the expert will suggest a particular action. You want to develop an algorithm, a machine learning model that is actually making another action, and you want to minimize the distance between these two actions. So the idea is to, there is an expert, so this is the context of the too slow side. So there is an expert that is actually able to tell me what is going to be the optimal or close to optimal decision, except that maybe it's taking too much time. So I want to develop something which is much faster in making the same decision by imitating the expert, okay? So this is actually what we call demonstration, is most of the time, the best method, the best models, machine learning models are making a significant use of neural networks. And this is a particularly good context if you have an expert that is actually telling you what to do. On the other hand, sometimes you don't have the expert. And so by learning by experience is the right thing to do, in which at the time of the decision, you recommend an action, the algorithm ML recommend an action, recommends an action, there is collects a score, and the overall goal is to maximizing the return, so the overall reward associated with the learning of this particular action. This is saying learning by experience, and this is done in the context in which you don't really know what is the best. You don't have an expert, or at least you want to go beyond the expert. And by demonstration, you will stick with the quality of the expert you're using. By doing experience, you can, let's say, work with an initial expert, but then if you develop something in this kind of reinforcement learning type of approach, then you can go beyond what the initial expert is about. Of course, experience and learning in this way should remind you of AlphaGo, for example, which has been the biggest back in 2017, I think it was been the biggest success for machine learning at the time. So teaching an algorithm, a machine learning algorithm to actually beat the world champion of Go by developing a reinforcement learning method. So if you want to use aggressively machine learning, then you need to be aware of the learning process that requires somehow to have an optimization algorithm or set of algorithms that are actually minimizing this objective function, which is the distance between the action of the expert and the action taken by the machine learning method, or are maximizing the return in an experience, learning by experience type of framework. Then you have hyperparameters, which are the ones that are at the core of the structure of the architecture that you want to use for learning. Then you want to break your system into training set, validation, and test set. You want to do good data collection. We talk about this a few things in the examples. We want to do avoiding overfitting, and you want to decide if doing learning online or offline at that point. I think Timo will cover some of this definitely in his talk. So the first thing, however, that you want to ask yourself when you develop something of this type is, what is the representation? So the machine learning has been particularly effective in the context of image processing, because the image is very well defined in these grids of 256 by 256, 512 by 512, and so on and so forth. So the idea is you have a very good representation of what you are working with. And the question is, how do you represent a MILP, right? I mean, our MILP is this guy here. Again, linear objective function, linear inequalities, and some requirements on the variables. And then how do you go from this representation to something that on which there is a powerful, let's say, representation from powerful machine learning algorithm to work on that representation. And it is not necessarily sufficient or fit for machine learning task at hand. This representation. And so the question is, how do you characterize the MILP? How do you represent it in order that the methods would have been developed or new methods can actually work as much as possible? And there are requirements or properties that will be particularly useful to decide your own representation of the problem. And these four properties are the permutation invariance. So the permuting the order of the variables and the constraints should not have an effect on your learning. Scale invariance, so you want to play with the numbers in order to make sure that you're staying within a controlled range. You want a size invariance, so the size of the representation should not depend on the size of the instance, and you want a low computational cost, because it's not about classifying one single image and deciding if it's a cat or a dog, but you may want to use this learning within a branch and bound, which means, like, for example, for variable selection, every time that you are having to make this decision, which sometimes is millions of nodes. And so ideally, the situation requires to be fast. So there are what we analyzing the literature with looking back, there are three type of representation which have been very popular in the use of learning in MILP or MILP. These are associated to three papers that are the one of Khalil et al. Back in 2016. So Elias and co-authors were looking at actually working for on branching, and they use what is called descriptors that essentially abstract a bunch of different characteristics into a vector of fixed size in such a way that the MILP, you can represent a MILP of different number of variables and constraints somehow into a unique representation. So those descriptors aggregate information whose length otherwise will depend on the problem size and make it actually condensing into one single, vector. And instead, the paper by Maxime Gass and co-authors back in 2018, still on branching, has actually worked on for the first time using a representation which is associated with the use of graph neural networks, which is a specific type of neural networks. And this is called a bipartite graph representation of the problem, in which you have a bipartite graph with, on the one side, the vertices are representing variables. On the other side, the vertices are representing constraints, and there is connection if a variable belongs to a constraint. I will go into the detail of this in a second. Finally, the paper by Giulia Zarpellon and co-authors take a different approach, where they're stressing the importance of the historical information collected within the branch and bound. So the idea is that it pays less attention to the structure of the problem and more attention to the evolution of the branch and bound itself in order to actually distill information on the go for understanding what is actually the evolution of the algorithm is. So during execution. So this representation is depending on the information and the three papers, is telling you where, so the lighter, the stronger the blue is. Here there is a very light blue, it's not white. Tells you how much this representation is actually tailored to that particular group of information, for example, objective coefficient and bounds, structural information about constraint coefficient statistics, LP solution, incumbent solution, tree statistics. As you can see, in the case of the paper by Giulia, the thing is that it's particularly tailored to actually use the three characteristics, so the pseudo cost, the conflicts, and other things like this in order to actually distill information about. So the so-called bipartite graph representation is the one that I just outlined. So if you take the problem written in not in compact form, so now is the linear objective function and the constraints. Before in compact form, they were written at AX less or equal than B. Now they are actually written in explicit form. You can recognize a bipartite structure in which I'm using the constraints on the one side, the variables on the other side, and there is the connection. A11 is the coefficient of variable 1 in constraint number 1. So by this representation, you can go from a graph, this is of course a bipartite graph, to actually what is called a graph neural network. The graph neural network works in this way. You have a d-dimensional graph embedding, Xi. If you have a function that takes the graph into account and the vertex, and one particular vertex, and returns an element, which is a Xi GV, that you can imagine as a vector of information of fixed size. So now the graph neural network is a function that takes an input, as input the graph and an initial embedding, which is obtained in this way, and defines a recursive embedding, C over T, over time, over the vertices. So repetitorily representing this means that if I have a vertex that's an input to the embedding, I'm going to produce an embedding for that particular vertex. And here I'm producing an embedding of the neighbors of this vertex, so 1, 2, and 3. And the graph neural network, what it does in this recursion is aggregating in linear terms the embeddings over the vertices, over the neighbors, and then combining this aggregation into the new version of the embedding itself. So CTV is the embedding of vertex V in graph G that goes from time t to time t plus 1. So this combination can be obtained, for example, through a feed-forward neural network, and one iteration of this is called the message passing. Of course, if you do more iterations of this, you get a better and better representation based on the embedding and more information related to this. And the more message passings that you are doing, the more time it takes. So coming back to the picture, so the structural properties of the constraint coefficients are implied in this representation because eventually you are taking all the neighbors of a particular node and putting them together and obtaining this representation in implied form. So once we have the representation, the question is, which are the learning tasks, right? So where do you want to improve your MILP technology based on machine learning? So the first area in reverse order with respect to the building blocks that I discussed before is primal heuristics. So a number of methodologies have been proposed for this purpose. And these methodologies are based on three different ideas. So the first one is you want to guide a heuristic search with the starting predicted solution. So you want to do some local search heuristic by within the MILP by first starting from a partial assignment, or you want to do a solution improvement with by learning in advance the neighborhood in which you want to work with, or you want to learn a schedule of the all the heuristics that you have in your MILP algorithm solver, and you want to order those heuristics and deciding how much time they should invest in finding feasible solutions. For A and B here, and the important concept is the one of large neighborhood search. So the idea is to optimize an auxiliary MILP or MILP. As you have realized, I'm using MILP or MILP at the same way. Of smaller size. So you want to restrict the size of your problem and looking at a neighborhood of eventually of one solution or a neighborhood of the problem itself by going deep in that particular place. And for both A and B, this is actually what happens. In the first context, so what we call A, primal heuristics or guiding a heuristic, the idea is to have a collection of initial solutions, having a machine learning algorithm which actually decides fixes some of the variables to values that they persistently happen to, for example, to be good in those solutions, and then you run a reoptimization over the rest. So whatever has not been fixed before. So these are several examples have been relatively useful, especially in graph type of algorithms, and it's very connected to the second side in which you are doing the neighborhood selection. So instead of fixing something a priori, what you're doing is deciding which variables, so it's one, say the complement of the other, you decide which variable you want to look at and how many variables to unfix and optimize them accordingly. So again, the definition of the neighborhood reminds kind of the idea of the large neighborhood search, but also of let's say of variable neighborhood search. So you, depending on where you are, you may want to decide of larger sizes of the neighborhood or smaller sizes of the neighborhood, and this can be learned by looking at the properties of the solution. And the third one is the idea of scheduling these heuristics. So imagine that like Skip, you have many type of heuristics inside. your solver, and you want to order them according to the best strategy for that particular group of instances, and running them not all for the same amount of time or amount of iterations, but according to this let's say, specific ideas and specific characteristics of the instance itself. So the ZIB has been the core of this research. Antonia wrote 2 great papers about this, and Endel as well. So I don't know if he's I don't see him in the audience. But anyway, so this is a lot of work has been done here at ZIB. So I'm switching gear, so primal heuristics and now variable selection. Definitely variable selection has been the area of MILP in which machine learning has been given the most attention, both by us, so MILP researchers and the machine learning researchers. And initially, the most of the effort has been concentrated on approximating strong branching. And so which is in this case the expert to imitate. So this is a picture here, a table in which you can see a bunch of papers starting from 2016 actually to 2022, even if there is still a lot going on, in which people were doing supervised or imitation learning most of the time. This is the type of objective function that they were using for the work. So, and offline or online in one case. There is one paper here of Alvarez et al. Is online, and also a paper by Khalil that is online. And where online means that you are collecting information during the branch and bound, and you are essentially changing your variable selection algorithm by the information you're collecting. Offline instead means that you are running a lot of experiments on a group of instances, on a class of instances, taking the information about those instances and devise a method that later on will be applied to instances of the same type. And I will talk about generalization in a second. About running things on a group of instances and reapplying it for the same class of instances is actually generalization. So to date, the algorithm that somehow is more powerful is the one developed or evolutions of the one developed by Maxime Gass and co-authors back in 2019, in which for the first time a graph neural network has been used for in combinatorial optimization, and in particular for making decisions on variable selection. And essentially, the idea in that paper, the strong idea in that paper is to use two strong ideas. The first one is to use graph neural networks to imitate strong branching, and the second one is doing this by behavioral cloning. So before that, behavioral cloning means that before that, the algorithms were trying to actually predict the score of strong branching, which means that for every variable, they will try to compute the improvement of the bound. This is actually very difficult in a certain sense because you are comparing objects which are, on which if you make a mistake, this is going to be problematic. While behavioral cloning here is to essentially says that you don't want to actually learn the score itself, but you want to learn the relative magnitude. So essentially ranking the variables according to which one is actually giving you potentially a good branching score. So in this way, this in the paper of 2019 and in the follow-up papers, for the first time, the authors were able to actually outperform reliability branching under certain conditions. So you're not counting too much, actually you're not counting the amount of time it takes to actually going from the neural network representation which runs on a GPU to actually the CPU representation of the problem. So the fact that the branch and bound itself runs on CPUs, which is one of the biggest issues. But under those conditions, time-wise and the number of nodes-wise, this is actually one, this is very competitive with reliability branching. So generalization, so the point that I wanted to make, is so far the methods which have been more effective are methods which are running, are devised, I mean actually designed for a class of instances. So you're training your method on a class of instances. And then the generalization is to run the same machine learning, so the shell is the same learner, to predict something on that particular class, maybe on larger sizes, okay? So now, so far, these methods are failing to generalize. So whatever I learn, whatever good, strong branching approximation I'm making for knapsack instances, this is not going to work per se on set covering instances. So I have to retrain the machine or my machine learning model in order that is going to be performing well on set covering instances. So in order to go farther of this situation, which is very common also for, I mean, for most of the methods so far developed in the area of machine learning for combinatorial optimization, two approaches have been devised. The one that I already talked about by Giulia Zarpellon and co-authors is essentially taking into account way more the information that is collected in the branch and bound, so the characteristic of the evolution of the branch and bound versus the structure of the problem. This somehow frees the situation of concentrating on the characteristic of an instance, of a class of instances, and goes to I mean, somehow moves to the generalization side. And the following, the subsequent step would be to go beyond the demonstration, because Giulia's paper and Lynn's paper are still working in the context of imitation learning. Going beyond the demonstration and learning by experience, which will be doing this in a reinforcement learning type of framework, which has been attempted. I mean, there are at least two papers by Etev and co-authors and Scavuzzo and co-authors in which they are following this path. We are very much at the beginning of the, I mean, scratching the surface of this type of approach. The difficulty is in reinforcement learning is to have a huge solution space to actually work with, and a very small signal in terms of very, let's say, weak signal in terms of the reward representation. So converging on the other two tasks, cat selection is a fundamental tool, as my colleagues have convinced you in the first week. And the area in which the people have been working on the most is cat selection. So I have a bunch of cat planes which have been produced at my favorite separation oracles, and I'm trying to get the best ones to work with. There is a nice recent survey by Elias and Deza, so I think he's a student, about the use of machine learning in for cat selection. And I think Timo will talk about this as well later. Let's say, I will not go too much into the details, but we are a little bit at the beginning of this. Single cat selection means that you want to decide among a group of cats the one that you want to add first. And there have been two papers looking into this question by Paulus and co-authors and Tang and co-authors, in which the first one is doing imitation learning, essentially doing the same thing that is done for strong branching, for learning strong branching. So you, instead of imitating the branching, you're imitating the cat, in the sense that you are adding one cat at a time, observe the LP relaxation after the addition of the cat, and then you pick the cat that you prefer based on this. So this is the learning scheme. In Tang et al., instead, what they are doing is reinforcement learning. So potentially they can go beyond this, but reinforcement learning is a complicated framework to actually run, to make converge. So again, single cat selection is a little bit, let's say, disappointing, in the sense that we know that we will never go one cat at a time. We will go for multiple cats at the same time. There is a little bit of research on this direction as well, but this is actually very much at the beginning. Finally, preprocessing. This is an area in which there have been instead and configuration a lot of good results. Like, I mean, this is the solvers are now including some machine learning methods that are telling them how to configure the system or how to actually make some of the decisions. I think Timo will talk about this in detail. The first one of those successes is the one of Pierre Bonamy and co-authors back in 2018 and improved in 2022 with the paper appeared in Operation Research, in which the authors prescribe a mixed integer quadratic programming instance if for mixed integer quadratic programming. So now we are going a little bit further, I mean, beyond mixed integer linear, and we're taking an objective function which is quadratic. They are looking into the question of linearizing or not the objective function. This is actually in Simplex default since version 12.10, and this has been like probably the first success of machine learning in commercial solvers used inside Skip now as a certain sum of them, not a commercial solver. Express, Gurobi, I'm sure they have something in the same realm. And this is actually some of the other successes, and I'm pretty sure that you have been covering this a lot. So let me use the last 2 minutes to tell you a little bit of perspective and challenges. So generalization. So this is a random IID pixel matrix. This is a random IID pixel matrix that is as a face. This is some website that was famous a few years ago. This is called This Person Does Not Exist. Is essentially allowed to put random pixels together in order to make something appear or not. So the question is similar to what we are looking at here. So this is you can think about a random IID coefficients of a matrix of a mixed integer linear program, except that they are not appearing randomly, right? I mean, whoever has any experience in running MILP solvers, you know that if you produce completely random instances, these instances are easy to solve. The problem are in the case in which there is actually a structure, which makes the problem more difficult on a certain side direction, and makes the problem, somehow okay to learn, right? I mean, we can learn some of the structure and we can exploit the structure according to what I've been discussing so far. The business perspective is the way in which we have been developing software for mixed integer linear programming in the last 30, 40 years is with this default version fits all. So like I'm developing the software in such a way that it can solve any instances the best possible way. We know that this is not how MILP solvers are used in practice, in the sense that the people are buying any one of the solvers will not solve one day TSP and the other day set covering and the other day knapsack. Unless they are consulting firms, they are generally using it for solving one particular type of application. So the question is how to leverage data in order to build on top of repeating solving the same problem over and over. And this is software that has been developed in conjunction with Skip, that by my team, and in particular Antoine Provost, that is called Ecole. And I'm leaving with this challenge and opportunity. The challenge is the use of neural networks, especially graph neural network, has proven effective for the learning tasks that have been considered, but the computation, as I said before, is happening on GPUs, while the MILP solving is happening on CPUs. So the interaction between these two architectures or computational environments is costly. And so this is somehow slowing down the use of machine learning in MILP. And the last thing that I wanted to say before giving time to Timo is we are using more and more restarts within MILP solving, so which means I'm stopping the computation and I restart the computation with different parameters configuration or different type of algorithms to run. And this somehow suggests that potentially one can use this initial runs or initial multiple runs in order to collect more and more information and making sure that this information is analyzed by machine learning and used for configure the system even more. And that's it for me. Sorry for this very fast run.